Welcome to Innovate and React. In today's episode, we will be talking about electrolysis and how this technology can be improved with theoretical chemistry and electrochemical improvements. Today, I'm with Usama. He's currently doing his PhD at the University of Duisburg-Essen in electrocatalysis. I'm very excited to learn more about how theoretical driven approaches can make better catalysts for water electrolysis. Welcome, Usama.
Hi, Kevin. First of all, thank you for inviting me on your nice podcast platform. As you have already told them that my name is Mohammad Usama and my journey, I want to talk about a little bit about my journey before because it is a bit unconventional, but I think that's what makes it more exciting. And that would also be motivation for someone who is trying to figure out their next step in their career, especially in academic career. So I started my academic career with Bachelor's of Mechatronics Engineering. I did from Pakistan Air University. Um, I was always fascinated with machines, robots, and how different systems come together. So that curiosity naturally pushed me toward exploring automobiles. So I went to UTM, University of Technology in Malaysia, to pursue masters in automotive engineering. During this time, I really enjoyed working with vehicle systems, simulations, and control design. Okay, so but at some point, I realized that I want to go even deeper to the atomic level. I started asking myself, okay, so what's really happening inside these systems we rely on? What happens inside a battery? Now even I can say inside the catalyst, what's really happened at the level of atoms and electrons. So that curiosity led me to the field of theoretical catalysis and electrochemistry, which I'm pursuing through my PhD at the Faculty of Chemistry in University of Duisburg-Essen, which is in Germany, in the group of Professor Exner. So in a way, my career has moved from a macro scale to the atomic scale.
Yeah, that's interesting because usually when people study chemistry, they go from the molecules and then somehow end up in the application later on in their jobs in the industry.
Yeah, that's top to down. I'm going down. Yeah, that's true. But that's the beauty of science and engineering. You look at the same problem. You look the same problem at very different levels of detail.
Yeah.
So I would say to the persons who wants to switch the fields or want to explore more, they just need to be curious and take a leap of faith.
Yeah.
But the important component is will. Yeah, if there's a will, there's a way.
Yeah, of course.
So that's a brief introduction of my journey.
Yeah, thank you. That is indeed not the classical way, I would say, but especially these interdisciplinary stuff, I think always brings more value to the whole discussion because then with your engineering background, you have now a different point of view on these chemical problems on the atomic scale, and that might bring new discoveries that other chemists with a classical background would not have thought about. So it's like this interdisciplinary research is always productive.
I don't know, but yeah, because engineers mostly think about the classical level, so they always want something hands-on. They do not just rely on the quantum mechanics or on the quantum level because they cannot see or imagine those things. But when you try to connect those things, so yeah, something really good happens. Sometimes, maybe most of the time, I don't know.
Yeah.
I can just comment on myself.
Yeah.
For me, it happened.
Yeah. And now we want to talk about the electrolysis and how catalysts are used to make this reaction more efficient. And maybe let's start with the basics. So the electrolysis we are talking about is the water electrolysis. Why do we need water electrolysis and how does it work?
Okay, before we talk about electrolysis, we need to know why do we need electrolysis, right? Why should we move towards electrolysis? For that, we should talk about importance of hydrogen because these days hydrogen is known as the fuel of future, but I would say it's more of a glue for the future energy systems. Why I would say that? Because it connects renewable electricity and with the sectors that are really hard to electrify. For example, heavy industry like shipping, aviation, automotive, etc. You can name any of them. Mostly the global hydrogen, I guess 90 to 95% global hydrogen is currently made from fossil
Yeah.
fuels.
Steam reforming.
It can be either, yeah, it can be either by natural gas via steam reforming, just as you said, or coal gasification in some countries like China, which emits millions of tons of carbon dioxide that is really affecting our environment
Yeah.
on a global scale. So if we want to shift towards the green transition, we really need clean hydrogen or green hydrogen.
Yeah.
Why we're saying green hydrogen? Because the hydrogen created by the natural gas or coal gasification is known as, I guess, gray or brown hydrogen. Gray is related to the natural gas, or brown is related to the coal.
Yeah, this whole
Yeah,
color schemes are a bit confusing,
yeah.
and I think it's a better way to think about just the CO2 emission that are caused by the
Emissions. Yeah.
different production
And for
methods.
that, I would like to emphasize here on the mini case study. There's, for example, let me share it. China produces about 33 million tons of hydrogen per year, mostly from coal gasification. That emits even more CO2, carbon dioxide, than the entire country of UK
Yeah,
annually. So this really shows that's the why is it really urgent to transition towards the green
yeah,
hydrogen.
that's a huge lever there.
Yep. Okay, so to encounter this problem, we need to come up with something which does not emit carbon dioxide on that scale, or should not emit even a little bit of the carbon dioxide. So that process in the field of electrochemistry, which is basically just how the electricity interacts with the chemical reactions, one of the key processes is electrolysis. So in electrolysis, we use electricity to split molecules into their building blocks. For example, in water electrolysis, just you talked about, we split water into hydrogen and oxygen. So electrolysis is basically a bridge between green electricity and green fuels.
Yeah.
Okay, but because I'm a theoretician, so I should also give you the theoretical perspective of electrolysis. What we try to do in electrolysis is to understand the fundamental reactions, how molecules interact with the catalyst surface, and how bond breaks, how bonds forms. So if we can understand these mechanisms deeply, we can design better catalysts and processes.
So in the electrolysis process, you need the
Mhm.
catalyst on the electrodes to basically get a better interaction between the water molecule and the electrons.
Yeah, to enhance the reaction and make it more faster and efficient because there are some challenges which we need to tackle. For example, these days or currently we're using expensive electrode. We're using the material iridium or platinum. Reactions have high energy barriers, which means that will require a lot of electricity, which means more cost.
Yeah.
So that's another problem. There's another problem about selectivity. You might have byproducts, so on. There are a lot of problems. I'm just listed just one, and I guess Europe, green hydrogen production. I just read it. I guess 1 year ago that it was 3 to 4 times expensive than the gray
Yeah.
hydrogen. So it is still expensive if we talk about even the electrolysis. So the big question is how do we make electrolysis cheaper, faster, and scalable? And that's where the catalysts come in, and that's the challenge in general.
Yeah. So better catalyst for cheaper reaction overall because you get a higher efficiency and then you can get a lower cost of the hydrogen in the end. Because like for the PEM electrolysis, for example, iridium is one of the key metals that is used in the catalysts, and That's very expensive, and therefore it would be great if we can reduce the amount that's necessary for the same reaction.
Yep, yep. That's where my work comes in. So, yeah. So why we are working with the catalyst, or how can we improve these reactions on the catalyst surface? So I'm a theoretician, so let me just tell you about why theoretical chemistry is important and how can we just improve these reactions. So let me just give you the introduction first. So what is theoretical chemistry and how does it work? So instead of building catalyst after catalyst in lab, which is slow and costly, theoretical chemistry basically lets you simulate those reactions on a computer. So you don't have to make catalyst and then try it and then see, okay, it's not, is it worth it or not, and the process goes on. So one can, okay, so that's the base of the theoretical chemistry, but there must be a level of theories because it's not just simple. You go in and you get green hydrogen. No, there are level of theories. We can start from molecular dynamics, meaning we simulate atoms over time. Then there are continuum models for large scale processes. Then there comes DFT, which we use, which is at the quantum scale. So let me tell you about the
What
DFT.
does the
Okay.
DFT stand for?
Oh, sorry, I didn't introduce it. DFT means it's a method known, and it stands for density functional theory. You can think about DFT as a quantum microscope. It basically allows us to see how electrons move and the bond forms and breaks at atomic level. And that's the simplest definition.
So yeah, it's very deep look into the reaction.
Yeah. So you can predict how the catalyst will behave before you even make it. But we can go beyond DFT, just like in my work, we have gone beyond DFT, density function theory, to use GAN canonical because we need to account role of potential because it's
Yeah.
electrocatalysis. So there's a role of electricity. So we need to account for that. Then, as we are moving towards artificial intelligence, so there are also some techniques or methods about to find out the transition states using machine learning, nudge elastic band. So you can find out the transition states using those methods, which are really efficient. So that's you can connect thermodynamics with kinetics, and you can also have the influence of the solvation and the gas phase. So DFT isn't just about static calculations. It's becoming more smarter in dynamics. Yeah, thanks to the advanced frameworks and machine learning, of course. So in short, I would say that theory isn't replacing experiments. It's just guiding them, telling us which ideas are worth testing and which are dead
Yeah.
ends.
It already
So
narrows down which catalysts to look at more closely and which are basically a moot point because they,
waste of time.
yeah, exactly, because they don't have any activity anyways. And do you think it's sometimes more obvious than in other cases that you can say, okay, here we don't really know if it's really great, so we have to test it in lab? Or do you already have clear winners and losers, I would say, in like the catalyst, and then you can say, okay, these are out when we look at those?
I think it's never a one line answer. It's never easy to just say, okay, this one is not worth it. And this, because every method has caveats and pros and cons, of course. So sometimes experimentalists synthesize something and that's not even in the theory, but
Yeah.
sometimes it's the other way around. So you cannot just exclude anything on a basis of simple rule.
Yeah.
So you need to explore more. For example, in my case, as I worked with, or as I am working with iridium dioxide, which is known as the best OER catalyst because of its stability and, of course, activity. But there might be other materials which can perform as same as iridium dioxide, but we haven't explored that yet.
Yeah, that would be great.
So that's one of the purpose. Yeah, that would be great because iridium is very much expensive and it's rare.
Yeah.
So, and that comes to the purpose of my work because we are trying to benchmark those standards because as it is the best catalyst under anodic conditions, or we can say, of course, in acidic conditions, because it does not corrode easily.
Mm-hmm.
Okay, if we explore all the properties that are related to the iridium dioxide,
Mm-hmm.
especially 110 facet on which I'm working, one can ask, okay, what is 110 facet? So 110 facet is basically well defined. It exposes reactive motifs. We can model reliably. So it reflects catalytic behavior seen under operating
Mm-hmm.
conditions. Okay, so it would be a right model to surface to uncover. Mm, yeah, it would be right model to uncover principles we can transfer later to the cheaper earth abundant systems.
Mm-hmm.
That's one of the goal that's why we used iridium dioxide 110 in our study.
Mm-hmm. So you want to find out all its properties in very much detail, and then you can later on check which other systems have similar properties, so they could also perform similar in this reaction.
Similar to,
Yeah.
yeah,
Okay.
that's one of the goal. I cannot say that most of the all the property, but I can
Yeah.
say like pretty much. Or we can say that we have set a basis of it,
Mm-hmm.
so others can apply and build more on it.
Mm-hmm. So now we know how the DFT and the theoretical chemistry can help to identify possible catalysts. And yeah,
Hmm.
let's look a bit more about your reaction, what you did. You already mentioned the oxygen evolution reaction, which is part of the
Yeah.
whole electrolysis process. Why did you look at the oxygen evolution reaction and not the hydrogen side?
Yeah, that's a really good question. Okay, so water electrolysis reaction is really simple in theory,
Yeah.
that water dissociates into hydrogen and oxygen. But it's very difficult to efficiently do it.
Mm-hmm.
The bottleneck is oxygen evolution reaction. It's where the most of the over potential and efficiency loss happen.
Mm-hmm.
So that's a really big problem. That's why I'm investigating OER.
Yeah.
Its equilibrium potential is quite high than the hydrogen evolution reaction. So we need to tackle this problem first, so we can make the other process efficient.
Mm-hmm.
That's why we chose to do investigation on OER,
Mm-hmm.
specifically on iridium dioxide. That's I have already explained. Then we can come to the okay. So you have water and you want to have the oxygen. Let's define the first point as point A and the second as point B, and you have to go from point A to point B.
Mm-hmm.
It can have multiple ways to go there. It
Yeah.
can be just straight line, it can be just you go haywire and all the way around. So it can be anything. That's a very naive example, but one can understand from it. So in one part of our work, we systematically compared the conventional OER mechanisms which were already present in the previous studies. For example, mononuclear, bifunctional, etc. There are, I think, seven mechanisms.
The mechanism for how the oxygen evolution reaction takes place on the catalyst.
How the oxygen evolves,
Okay.
yeah.
Mm-hmm.
Yeah, in simple words, how the oxygen
Mm-hmm.
evolves on iridium dioxide 110
Mm-hmm.
surface. So, yeah, even there are reaction mechanisms for OER, for iridium dioxide, of course, but it's not settled yet due to there are a lot of contradictory reports in the literature about the mechanisms. Okay, one says this OER will happen by this mechanism. Other says no, this will happen by this mechanism.
Yeah.
So there's not a consensus in the reports.
Mm-hmm.
And also about the rate determining step, it was always related to the formation or okay, I haven't told you about the simplistic mechanism of the OER. It is four electron proton transfer step.
Mm-hmm.
So there are three intermediates which needs to be formed: OH, then OOH, then the O2 dissolve. That's a simple mononuclear mechanism.
That is how many electrons are used up in this process.
Yep, to make oxygen from a water.
Mm-hmm.
So it's four-step
Mm-hmm.
process. water dissociates into OH, then this OH dissociates into O, then the another water attacks, so it makes OOH intermediate, then OO combines to make oxygen molecule, and there's a release of one proton.
Okay, and each of these steps consumes some electrons, and that's in total.
Electrons and
Yeah,
protons,
okay.
and release some proton. Yeah. So that's the process. Okay, so what we did, we tried to explore all those mechanisms on different surface configurations. Okay, what I mean by surface configuration is that which surface of iridium dioxide 110 facet is thermodynamically more stable. And that can be found out by surface 4-bay diagram. So we found out, and we found out that uh, the most thermodynamically stable surfaces are from fully hydroxylated to the oxygen covered, or it can be either OOH terminated. So even though we find out that it would be a mixed surface, that would be the most stable surface, but we chose the other one also to see, okay, what if we change the surface environment, what happens? So we chose 4 different surfaces, which I have told you.
What are the main differences between these surfaces?
Okay, one can be fully hydroxylated, means more hydroxylated. One can be partly hydroxylated. Then there can be only oxygen covered, and
Okay.
there's one more which can be OOH terminated. That's partly OOH terminated. So we wanted to see the effect of those. If we change the surface environment, what happens with the activity of the OER?
Okay.
Okay, so we chose those surfaces and did all the mechanisms investigated through GMAX, the catalytic descriptor, and found out all the what were the differences in those mechanisms on those surfaces. But there was another pathway we included in the second part of our paper, which is known as Walden-type pathway. This term comes from the homogeneous catalysis, the SN2 reaction, where the reactant comes and product goes out in the simultaneous step at 180 degree. But in heterogeneous catalysis, in which we work, it's different. It does not happen at the 180 degree, but the process is the same. Reactant comes in, product goes out. So that's why we called it Walden-type pathway. It's not Walden inversion. So the process is the same. And the second thing, mostly in the previous studies, this iridium surface site becomes vacant whenever the product is formed. When O2 is formed, there will be a vacant site. But in this reaction, a Walden-type pathway, in this mechanism, it won't be the vacant site. It will always be, because the reactant is coming in, product is going out, so there's no space for to become vacant site.
Yeah, it replaces it directly.
Yeah, so that was thesis of our paper, that this mechanism really enhances the catalytic activity, and that's implicate that the OER on iridium dioxide may not proceed purely through the kind of classical mechanisms we have assumed for years, but through this simultaneous adsorption of product O2 and reactant H2O pathway, known as Walden-type pathway, which is thermodynamically and kinetically favorable. And we explored with the methods to support our study. We used the methods and DFT calculation, which was implemented in WASP. And we explored not only the thermodynamics, but also the kinetics through the nudge elastic band calculations. And we also included the solvation and grand canonical effects to mimic the electrochemical environment. And the catalytic activity, I have already mentioned that it was calculated through the GMAX descriptor, which was proposed by my supervisor. One can read about it in ACS catalysis paper to find out why is it better than the conventional thermodynamic overpotential as a descriptor.
So it replaces in your calculations descriptor that was previously used, and now your supervisor proposed this GX.
GMAX, yeah.
To better describe the reaction mechanism?
No, the catalytic activity.
Yeah, the catalytic
So
activity, right.
yeah, before mostly thermodynamic overpotential was used, which just relies on single intermediate, which is the highest, or we can say the potential dependent step,
Mm-hmm.
which is the highest one, or we can say the which takes the most of the
Mm-hmm.
energy or requires the most of the energy to proceed. But this Gmax is special because it does not only rely on thermodynamics, it also approximates the kinetics
Mm-hmm.
into it, and it does not rely on just on a single step.
Yeah.
It can take multiple steps, so it kind of span model activity catalytic activity
Mm-hmm.
descriptor. So we used this one and found out that the Walden-type pathways provides a better catalytic activity than the conventional mechanisms.
Okay, interesting. So you basically use this descriptor then to improve your calculations.
No, that's just a descriptor. What improves our calculation is the DFT calculation and how we deal with it. We get the energetics and we calculate the free energies. And by using those free energies, we use this descriptor Gmax and found out which one is providing better catalytic activity,
Okay.
or it's providing it's better for the scaling, I would
Yeah.
say.
Okay. Yeah, this whole electrochemistry is rather new for me. I just did conventional homogeneous catalysis in my PhD.
It is also new, but I cannot say anymore. It's new to me. It was new to me 3 years ago, but now I can say, okay,
Yeah.
I'm not new.
Yeah, but that also shows that one can relatively quickly learn new things and then actually become an expert in this, like you did with this electrochemistry. And for future applications of this, did you already also validate your calculations in the lab, or are you collaborating with other labs to see if the mechanism you looked at is actually then what's happening also in the reaction?
Not directly, but there are some studies which shows the formation of or support these
Mm-hmm.
results, and also the change of potential rate determining step. That's the game changer, because most of the studies in the previous era was on the formation and decomposition of OOH intermediate. But in our case, it was about the formation of or decomposition of O
Mm-hmm.
intermediate. So that's really changed the game. And I have explored a little bit in the literature. There are some studies which really shows that there's a formation of O. So we are right on track, but we haven't yet collaborated with the experimentalists to really find out or validate
Yeah.
this result yet.
Mm-hmm. Okay, and that's already promising then. And
Yeah.
now, when you see these calculations, what is your next step in improving the catalyst?
That's an interesting question, because I can share my experience using not AI but data science or data
Mm-hmm.
analytics schemes or techniques to find out the same catalytic activity on a reaction known as nitrogen oxidation reaction, which is basically direct conversion of dinitrogen to the nitrate
Mm-hmm.
from the air by using electrochemical processes. But the caveat is that that process requires 10 steps, just like we for the OEI it was 4 step for electron proton
Mm-hmm.
step. It is 10, so
Mm-hmm.
it's really
Yeah.
huge. If you start doing the DFT calculation, so it's too much
Okay.
for that. And just imagine if you're doing with a different surface configuration, so that's not just 10, so that will become 40, and you need to explore more. If you have a big phase
Mm-hmm.
space, then you need more. So it's a hell lot of calculations.
But that's also for this reaction really interesting because it's basically then electrifying the Haber-Bosch process, right?
Yep,
Which
yep, yep,
also
yep.
contributes to, I think, 2% of the worldwide emissions.
Well,
And that's huge.
yep,
So if you could cut this, that, yeah.
yep. So basically, in this project, we use this data analytics and statistical methods to screen and analyze this huge amount of data that we produce using a data-driven methodology.
Mm-hmm.
So this allowed us to identify design criteria and predict cases where the selectivity towards NOR is greater than 90%, or in our case, we found out the 98%, in comparison with side reaction OER, because that's a bad guy there too. OER is also a bad guy there because it is a bottleneck process, because it falls in the same potential window that is thermodynamically and kinetically favored over the NOR. So that's really hard.
So in that case, you want to avoid the oxygen evolution reaction,
Yeah,
whereas in the water electrolysis, you want to have the oxygen evolution reaction as fast as possible.
yeah, we need to compress it or make it more
Yeah.
efficient so it does not get a lot of electricity or the heat and any other losses, so we can have more green hydrogen.
And in the nitrogen oxidation, you
Oh,
want to avoid it.
yeah,
Okay.
in nitrogen oxidation reaction, we need to avoid it. So, so it's not a rule of thumb, but it's obvious that if you want something, you need to suppress
Yeah.
the other. So, yeah, so I would say that these statistical or AI methods are really guiding chemistry. We are moving towards data-driven discovery from trial and error
Yeah.
method. It's not trial and error method anymore. We can quickly find or identify promising candidates and focus experimental efforts more
Yeah.
effectively.
Yeah, I think that is really a huge deal for the chemical research, because chemical research compared to other fields is very expensive, because you need a hell lot of chemicals, materials, also the instrumentation. And if you can
Yeah.
already narrow down the experiments you have to do with AI by your data
Hmm.
driven approaches, that already makes this
Hmm.
whole research more cost efficient and faster, probably.
Yep. So currently we can say that we are starting to use AI models to analyze large data sets, just
Mm-hmm.
like we did, and predict catalytic performance. But in the near future, we will move towards generative AI for catalyst discovery.
Mm-hmm.
Um, I'm excited.
Yeah.
Where models don't just analyze, but also propose new materials with targeted properties.
Oh, okay.
That's too early to
Yeah.
say, but that would happen.
Yeah.
We will see that.
I mean, we have seen how fast these generative models for
Yeah.
text evolved over the past few years. And so I'm
Yep.
also
Yep.
fairly confident that this will go to chemistry and improve the research trail.
Yep. And secondly, I would say that the data driven methodologies for screening is really good because instead of testing catalysts one by one, the trend is more towards automated
Mm-hmm.
computational pipelines that can evaluate thousands of materials virtually
Mm-hmm.
and narrowing down the best candidates before experimental validation.
Yeah.
That would be a nice technique to have in the near future.
Mm-hmm.
The guys are really already working on it. So, and the last one, which is really, I'm not saying in the near future, but we will see one day. It's about the integration with the industry using the digital
Yeah.
twins. So you can expect that AI and modeling can continuously optimize the performance and durability in real time. This will connect theoretical work directly to the industrial
Mm-hmm.
applications. So to conclude this one, I would say that I believe the next decade will see theory, AI, experiment converging into a single powerful engine for catalyst
Mm-hmm.
discovery, and that would really accelerate the discovery, which will, of course, shape our technologies for the future.
Yeah, definitely. There's also, I think, in the UK, it was a startup that is trying to implement also automated labs, where you basically have
Mm-hmm.
a reaction you want to optimize, and then you not only let AI choose which reactions to do, but you also have a or in their case, what they want to achieve is a fully automated lab where you can also do
Mm-hmm.
the screening reactions of these proposed parameters. You can just do
Catalyst.
them
Yeah,
with robots, and then you just have to basically give the right chemicals into the system, and then it will combine
mm-hmm.
everything in the way you want it, and then you get data so much faster compared when you have to go to the lab yourself and then do all the experiments and then analyze
That's
them.
really
And
cool.
yeah, so
But I would also like to add here an important note that we should not, we should also be realistic about AI, today's AI in catalysis, because it is still limited by the quality of data,
yeah,
and it does not capture all the parameters we require. So, yeah, but we should be optimistic because in the we are living in the broad era of AI. There are three eras: narrow AI, broad AI, and general AI. So we are in the broad AI, and the researchers says that in around 2040 or around that 2040 or 2045, we will be in the general
hmm,
AI. So that would be the era in which we'll see the digital twins and all the generative AI will be like the cognition of AI, I would
yeah,
say. So for these days, I guess everybody knows about the super intelligence. Yeah, GPT is working on that and all that kind of stuff. We will see that.
yeah.
I want to see that
Yeah,
how it will work.
yeah, it's super interesting, but also kind of scary when you think about it, because
Yep.
all this research that chemists are doing now then could, to a huge degree, also be done by uh, machines and these AI models, which make a lot of jobs then obsolete, because why would you hire chemists and then do all this work when an AI can do it for you? So I think that's also will be very, very difficult to have all this AI alongside the humans, I guess.
Yep, that's augmented intelligence where human and computer works together
Yeah.
to achieve fair or I would say the real AI, like in the general AI, they need to pass five pillars. I read about it. I was and because these days I'm also reading a lot more about AI
Hmm.
because you need to have these skills if you want to stay in the
Yeah.
game. Otherwise, you will struggle. So these are you need to be interdisciplinary. You can be, but you will feel I would say alone after some time.
Yeah.
Yeah, so it's better. So there are five pillars, and it's about AI ethics. It needs to be fair, robust, and explainable,
Hmm.
transparency, and privacy. So I would just focus on the biasness because it depends on the data that and the biasness comes from the data. So that's really a big
Yeah.
problem because you need to feed the data into the model,
Hmm.
right? So if the data is already biased, so you will get results what you want to see.
Mm.
That would not
Yeah,
be
that's a good point.
unbiased
Yeah.
data. So that's a big problem, and there are a lot of more problems there in the AI ethics. But the researchers will come up with
Yeah.
something, something to avoid these
Yeah.
problems.
Yeah, it's a very quickly moving field. I'm excited to see what will happen in this field that will probably bring some huge findings in the future.
Yeah, yeah, sure.
Okay, so to wrap up this discussion, as a final question, what is your favorite discovery in chemistry?
uh, that's that's a tricky question. I can easily pick something from catalysis, but honestly, what really fascinates me is the discovery of neurotransmitters
Hmm.
like dopamine and serotonin.
Yeah.
These are the molecules that like literally shape how we feel, how we connect, how we experience the world. So, as someone who spends so much time studying molecules on matter surfaces, I find it fascinating that tiny molecules in our brain can drive something as big as human emotions
Yeah.
and intelligence, of course. So, it's a reminder that chemistry isn't just about energy and reactions, it's also about who we are.
Yeah. And that's
Yeah, so yeah.
great concluding sentence for this episode. Thank you very much for taking the time and telling me more about your research.
Thank you for having me on the podcast, and I hope I was able to give a glimpse into the fascinating world of theoretical catalysis and its potential for shaping the future.
Yeah, thank you very much. Also, thank you for listening. If you liked this episode, don't forget to share it and hit the follow button. This really helps the show. If you also would like to be part of a future episode, contact me either on LinkedIn or send me an email to contact@innovateandreact.com. Until next time, keep innovating and stay curious.